Hello friends, I am Mr. Adeesh Deshpande from Fergusson College. We are discussing ionic equilibrium. We completed conceptual theories of acids and bases and Oswald's dilution law for weak acids and weak bases. Now let's consider towards next part of the chapter. Now in the earlier case, we saw Oswald's dilution law for weak acids and Oswald's dilution law for weak base. Also, we saw some of the numerical problems based on Oswald's dilution law. Now, as I told in the earlier class, that we deal with the aqueous solutions only. As far as laboratory is concerned, we are using aqueous solutions, and so let us consider about our solvent, that is water. So water is a very weak electrolyte and dissociates poorly to form very less number of H plus and OH minus ions. So here is the equation given. H2O liquid plus H2O liquid reversibly gives H3O plus aqueous plus OH minus aqueous. So as water is a very weak electrolyte and upon dissociation equilibrium is attained, let us apply law of mass action to this equilibrium to calculate equilibrium constant. So capital K is equal to active mass of H3O plus into active mass of OH minus upon active mass of H2O liquid the whole square. Now as compared with the concentration of water, concentrations of H plus and OH minus ions are very low since it is a poor electrolyte as we saw. And so denominator we can take constant. And so K is equal to active mass of H3O plus into active mass of OH minus upon constant. K into constant is a new constant called as Kw, and so expression is Kw is equal to active mass of H plus into active mass of OH minus, where Kw constant is called as ionic product of water. So what is ionic product of water? It is actually equilibrium constant. How it is calculated? On the similar lines by applying law of mass action. But since this is a solvent and dissociation equilibrium of only pure water is considered, and so this constant has given a special name called as ionic product of water. Symbol is Kw. So definition is numerical product of molar concentration. The numerical product of molar concentrations of H plus and OH minus ions at equilibrium in pure water at a given temperature is known as ionic product of water. So same mathematical definition we just wrote in the form of words. So these are molar concentrations of H plus and OH minus ions. These are equilibrium concentrations, their numerical product and at a particular temperature. So this is called as Kw or ionic product of water. Now its value at 298 Kelvin is 10 to the power minus 14. Now how to calculate this value? Experimentally, it is found that 1 mole of H plus and OH minus ions are present in 10 raised to 7 dm cube of pure water at 298 Kelvin, and hence concentrations of H plus and OH minus ions, they are calculated as number of moles upon total volume. Number of moles 1 mole are found in 10 raised to 7 dm cube. So 1 upon 10 raised to 7. So concentration comes out to be 10 raised to minus 7 moles per dm cube. Substitute in the expression of Kw. So Kw is equal to active mass of H plus into active mass of OH minus. So 10 raised to minus 7 into 10 raised to minus 7. So it is 1 into 10 raised to minus 7 mole square dm to the power minus 6 at 298 Kelvin. Conventionally, the unit of ionic product of water is not written, and so Kw is equal to 1 into 10 raised to minus 14 at 298 Kelvin. So this point you have to remember. Now, nature of the aqueous solutions. We know that pure water is neutral in nature. Now, under Oswald's dilution law, we saw that acidic nature of the solution is due to the presence of H plus ions, and basic or alkaline nature of the solution is due to the presence of OH minus ions. But now, water is the substance which contains both these opposite characters together, and these opposite characters are always present in equal proportion, equal amount, and so pure water is always neutral. And so for neutral solution, concentration of H plus ions is exactly equal to the concentration of OH minus ions in moles per dm cube. In case of acidic solution, H plus ion concentration is greater than OH minus ion concentration in moles per dm cube. And in alkaline solutions, H plus ion concentration is less than OH minus ion concentration, or OH minus ion concentration is greater than H plus ion concentration in moles per dm cube. This is how we can classify the aqueous solutions. Now let's consider one of the interesting term that is called as pH of a solution. So here is the mathematical symbol or relation given. pH is equal to minus log to the base 10 molar concentration of H plus ions. So pH of a solution is defined as negative logarithm to the base 10 of molar concentration of hydrogen ions in the solution. Similarly, another term is pOH of a solution. So pOH is minus log to the base 10 molar concentration of OH minus. So it is negative logarithm to the base 10 of molar concentration of hydroxyl ions in the solution. Now in the symbol pH or pOH, P stands for potens. Potens meaning strength. So pH indicates strength of hydrogen ion concentration expressed in moles per dm cube in the solution. Now why we require this pH and pOH? Students, in the laboratory, if suppose I give you two solutions, and if suppose I ask you to find out how much H plus ions or how many H plus ions and OH minus ions are present in these solutions, then it is very difficult to find out H plus or OH minus ion concentration. Theoretically, according to Oswald's dilution law, it is possible to calculate. But then in the laboratory, it is required, or a practical tool is required, experimental tool is required to find out actual H plus and OH minus ion concentration. And so in the laboratory, we are going to use these concepts, that is pH and pOH of a solution. Now the relation between pH and pOH. Now according to the mathematical definition of ionic product of water, so it is Kw is equal to active mass of H plus into active mass of OH minus. Substitute its value at 298 Kelvin. So active mass of H plus into active mass of OH minus is equal to 10 raised to minus 14. Now we are going to consider relation between pH and pOH. And so let us take log to the base 10 on both the sides. So log to the base 10 active mass of H plus log to the base 10 active mass of OH minus is equal to log to the base 10 10 raised to minus 14. Change the sign. So minus log to the base 10 active mass of H plus into bracket minus log to the base 10 active mass of OH minus is equal to minus log to the base 10 10 raised to minus 14. Now on the left hand side, you will find that these are nothing but the definitions of pH and pOH. So replacing those terms by pH and pOH, on the right hand side it will be 14 log 10 to the base 10. So pH plus pOH is always equal to 14. Now Sorensen's pH scale, a scale which helps to know the nature of the aqueous solution, whether it is acidic, alkaline or neutral, is called pH scale. So as I told earlier that in the laboratory it becomes easier for us to find out the nature of the aqueous solution, and so this pH concept is quite important and pH scale is also important. So in this scale, you will find that pH starts from 0 and ends at 14. Why it ends at 14? Because we have the relation between pH and pOH. pH can be maximum 14 or minimum 0. And similarly, pOH can be maximum 0 or maximum 14. So corresponding H plus ion concentration is also written below this. So when pH is equal to 0, H plus ion concentration is 10 raised to 0 moles per liter. When pH is equal to 1, H plus ion concentration is 10 raised to minus 1 moles per liter. Likewise, when pH is equal to 12, corresponding H plus ion concentration is 10 raised to minus 12 moles per liter. So for neutral solutions, H plus ion concentration is equal to OH minus ion concentration in moles per dm cube. So pH is equal to exact 7. For acidic solution, H plus ion concentration is greater than OH minus ion concentration in moles per liter. So pH is less than 7. And for alkaline solutions, OH minus ion concentration is greater than H plus ion concentration in moles per liter. So pH is greater than 7. So this is the pH strip. This strip you saw in the laboratory last year when we consider the experiments related with the pH. You saw this strip in the laboratory. Now, according to this strip or according to this pH scale, one point you can understand that if you know pH of a solution, you can calculate pOH. So for the same solution, both the values can be found out because pH and pOH are related with each other. Similarly, if you know pOH, you can calculate corresponding pH. And if you just go through the definitions of pH and pOH, what is the definition of pH? pH is equal to minus log to the base 10 molar concentration of OH minus or molar concentration of H plus ions. So H plus ion concentration can be found out as a 10 raised to minus pH. Same thing. Similarly, definition of pOH is equal to minus log to the base 10 molar concentration of OH minus. And so OH minus ion concentration is equal to 10 raised to minus pOH. And so if you know pH or if you know pOH, you can calculate H plus ion concentration and OH minus concentration also for the same solution at the same time. And so this is the use of Sorensen's pH scale. Now here are two examples how actually it works. For suppose you are given 0.04 molar HCl solution and you have to find out its pH. Then use the definition directly. pH is equal to minus log to the base 10 molar concentration of H plus ions. So substitute concentration of H plus ions. It is 0.04 molar, that is 4 into 10 raised to minus 2 molar. Now HCl is a strong acid. So H plus ion concentration is same as that of concentration of acid. So I substituted. pH is equal to minus log to the base 10, 4 into 10 raised to minus 2. Now keep the negative sign outside and split the log term. So what it becomes? pH is equal to minus sign outside into bracket log 4 plus log of 10 raised to minus 2. Now log 4 according to the log table is 0.6021 and log of 10 raised to minus 2 is simply minus 2, isn't it? Log of a raised to x, according to the rules of the logarithm, its value is x log a. But what is a? A is 10. Log 10 to the base 10 is always 1. so that x is minus 2, so that appears over here. Now multiply by negative sign and then or apply that negative sign, pH comes out to be 2 minus 0.6021 and so pH comes out to be 1.3979. So to find out pH by knowing the concentration of H plus ions is very simple, it's very systematic. Just use the formula as it is and just go on simplifying. Now in this case, second case, HCl solution is given whose pH is equal to 2. Now you have to calculate corresponding H plus ion concentration. And so using the definition, pH is equal to minus log to the base 10 molar concentration of H plus. But by the basic definition of logarithms, I can also write this formula as H plus ion concentration is equal to 10 raised to minus pH, isn't it? And so, if we have this simple relation, H plus ion concentration is equal to 10 raised to minus pH, just substitute given pH is 2, so H plus ion concentration is equal to 10 raised to minus 2. Now, once you calculate H plus ion concentration, in case of this HCl solution as 10 raised to minus 2 moles per liter, find out OH minus ion concentration. How? By applying the expression of ionic product of water. What is the expression? Kw is equal to active mass of H plus into active mass of OH minus. Substitute 10 raised to minus 14, the value of ionic product of water. Now H plus ion concentration we calculated as 10 raised to minus 2 and so OH minus ion concentration comes out to be 10 raised to minus 12 moles per dm cube. Now here one may raise a question that how we use this expression of ionic product of water since this is HCl solution. Then remember students, this expression for ionic product of water is used everywhere in all aqueous solutions, not just pure water. But why we studied that, why we found out that mathematical value, it is because it is applicable everywhere. For HCl solution, yes, you can use that expression of Kw. In case of NaOH solution also you can use that Kw expression. Because HCl solution, how it is prepared, you have taken HCl and you added water. As water is also present in that solution, you can use the expression for Kw. This is what is the use of Kw. Now, HCl solution is acidic, as we know. But according to these concentrations of H plus and OH minus ions, now we calculated both the concentrations. Just compare these values. 10 raised to minus 2 moles per liter H plus ion concentration and 10 raised to minus 12 moles per liter OH minus ion concentration. Which value is greater? Remember, minus 2 is greater on number line. We can remember the number line. So 10 raised to minus 2 moles per liter is quite greater than 10 raised to minus 12 moles per liter. This means H plus ion concentration is greater than OH minus ion concentration. So this solution is acidic in nature. So this is what we studied earlier in the theoretical part, which quite holds good when we consider practically example. So practically HCl solution is acidic, that we know. If you dip blue litmus paper, it turns red. And so same holds good with the help of the numbers. These are the concentrations in front of you. Now once we know OH minus ion concentration, you can calculate corresponding POH. Use the definition of POH because now we have OH minus ion concentration. And then you will find that POH comes out to be 12 and pH comes out to be 2. So relation between pH and POH also holds good in this case. So this is how this concept of pH and POH works. Let's consider the case of base now. For suppose 0.003 molar NaOH solution is given. and you are asked to calculate pH. Remember, pH and pOH, they are the two sides of a coin. So as NaOH solution is given and you have to find out pH, what you have to do, you have to first find out pOH, and once you know pOH using relation between pH and pOH, you can calculate pH. So let us first calculate pOH in this case. So definition is pOH is equal to minus log to the base 10 active mass of OH minus. Substitute the concentration of OH minus. Again, NaOH is a strong base. So given concentration of base itself is the concentration of OH minus ions. So pOH is equal to minus log to the base 10, 3 into 10 raised to minus 3. Now keep the negative sign outside, split the log term. So pOH is equal to minus into bracket log to the base 10 of 3 plus log to the base 10 of 10 raised to minus 3. Log 3 from logarithmic table is 0.4771 and another term becomes simply minus 3. So pOH is equal to 3 minus 0.4771 multiply by negative sign. So pOH comes out to be 2.5229. Now use the relation between pH and pOH as we have to calculate pH. So substituting, pH comes out to be 11.4771. So pH greater than 7 is the case of alkaline solution. pH less than 7 is the case of acidic solution. As we saw in the earlier case, pH was 2, HCl solution. And pH exactly equal to 7 is the case of neutral solution. So pH 0 to 6.999, any solution is considered as acidic because pH is less than 7. pH exactly 7 is the case of neutral solution, and pH greater than 7, that is from 7.0001 onwards up to 14, is the case of alkaline solution. Now consider one more example, NaOH solution whose pH is 10. Remember, NaOH solution is given and pH is given. So whether solution is of acid solution or base solution, convention is that always its pH is given. So pH is equal to 10. So pH greater than 7, and so it is alkaline solution. So find out first pOH to find out its OH minus ion concentration. So pH plus pOH is equal to 14. pOH comes out to be 4 from pH value given as 10. Now to calculate pOH, use the same definition. OH minus concentration is equal to 10 raised to minus pOH. So it is now very simple to know what is OH minus ion concentration. So OH minus ion concentration comes out to be 10 raised to minus 4 moles per liter. Now as I said earlier, use the expression of ionic product of water to calculate H plus ion concentration. So Kw is equal to active mass of H plus into active mass of OH minus. Substitute Kw is 10 raised to minus 14 is equal to active mass of H plus into OH minus concentration calculated is 10 raised to minus 4. So H plus ion concentration comes out to be 10 raised to minus 10 moles per liter. Now compare the two concentration values. OH minus concentration is 10 raised to minus 4 moles per liter. H plus ion concentration is 10 raised to minus 10 moles per liter. 10 raised to minus 4 is greater. So this solution is alkaline in nature. Its corresponding pH comes out to be 10. And so the given value of pH is 10. Whatever we calculated is also same. So this is how you are supposed to go through the numerical problems. So the first problem is calculate pH and pOH of 0.01 molar HCl solution. So HCl is a strong acid, so it dissociates completely in water as HCl aqueous plus H2O liquid gives H3O plus aqueous plus Cl minus aqueous. H plus ion concentration is concentration of acid given because it is strong acid, so it is 0.01 molar, that is 1 into 10 raised to minus 2 moles per liter. Use the definition, pH is equal to minus log to the base 10 molar concentration of H plus. Substitute on the similar lines, keeping negative sign outside, it is simply minus log to the base 10 of 1 is 0. So what remains is minus log to the base 10, 10 raised to minus 2. Simplify. So pH comes out to be 2. Once you know pH, calculate pOH using the relation. And so pOH comes out to be 12. Let's consider one more problem. pH of a solution is 3.12. Calculate the concentration of H plus ions. Now pH is given. So use the definition. pH is equal to minus log to the base 10 molar concentration of H plus. So pH is given now. So transfer the negative sign first. So what it becomes, log to the base 10 concentration of H plus is equal to minus pH. Substitute. So log to the base 10 concentration of H plus is equal to minus 3.12. Now here you have to make the adjustment. You cannot immediately find out the anti-log of minus 3.12 because this is a pure negative number. So what to do? Split that negative number, minus 3 minus 0.12. Then add 1 and subtract 1. So what it becomes? Log to the base 10 molar concentration of H plus is minus 3 minus 1, 1 minus 0.12. First two terms, second and next two terms. So it becomes bar 4.8. So minus 3.12 is equivalent to bar 4.8. And now H plus ion concentration is anti-log of bar 4.88. 0.88 anti-log is 7.586. Bar 4 is the power of 10. So 10 raised to minus 4 is the H plus ion concentration. Let's consider one more problem. Weak monobasic acid is 0.04% dissociated. In 0.025 molar solution, what is the pH? So percentage dissociation and concentration are given. Let's first calculate alpha. Alpha comes out to be 4 into 10 raised to minus 4. Let's calculate H plus ion concentration because that is required to calculate pH. H plus ion concentration is calculated as C into alpha. Substitute concentration 0.025 molar. So that is 10 raised to minus 5 molar. And last step is to calculate pH. So pH comes out to be 5 since using the same formula for pH. So students, in this class, we saw pH and pOH of a solution, Sorensen's pH scale, and some of the numerical problems based on pH and pOH of a solution. Thank you.